5.2 natural log function integration. We do the inverse operation, which we did yesterday. We learned differentiation of log functions, 1 over x, correct? And then if it was a composite function, it would be 1 over the stuff times the derivative of the stuff. We also called it u prime over u, right? Now, we're going to learn how to find the antiderivative of 1 over x. Well, since something's derivative is 1 over x, what's the antiderivative of 1 over x? Natural log x. But we got to use absolute value around the argument. We talked about if we needed to find the antiderivative of 1 over x dx, we could rewrite that and say x to the negative 1 power dx. Fine and dandy right now, right? Okay, let's find the antiderivative. We'll write down your base, add 1 to the power. That's okay, right? Divide by the new power. That's not okay, right? So that we have a situation where this happens. How do we take care of this antiderivative? Not by using the normal power rules, but by using logarithms, okay? So again, if we have a composite function, you make a u substitution. This is just, these two are very similar. X could be a composite function, but since we use u for the composite function or the inner function, we get that. But also, we know that when we take the derivative of a natural log function, you get u prime over u. If you clearly see that it is u prime over u, you can just go straight to natural log of absolute value u. I'll be very careful with this, though. That's just one of those small little tricks or quick ways of doing things that most of us would forget. We do remember how to go through the process of u substitution, though. Especially in a 3-hour test, you're mentally exhausted, you forget a lot of things, or you second guess yourself. You'll sit there and think about for 5 minutes. Well, in that 5 minutes, you should have done 2 problems already, right? Just go through the process. Some things that are tried and true, some methods that always work, and u sub is one of them. Now again, some of us will be able to remember this. We can go through these things a little quicker, save some time, do problems quicker, and we might recognize this pattern and go straight to it. But also, be very careful. The AP test likes to add just a couple little things in there to change it a little bit. Okay. Questions on this so far? Let's do some problems then. First one. We have to be able to recognize this as a 1 over x situation, and that means the antiderivative of 1 over x would be our natural log. Constant multiplier, I like to put that out in front, so I'd have 2 antiderivative 1 over x dx. And then our antiderivative of 1 over x is natural log absolute value x plus c. That's as easy as it gets, my friends. Go to the next one. Example 2. Now, I see example 2, and I always try and go through those processes of rewriting to make our lives easier, take the antiderivatives. But I look at this one, and I recognize right away there are 2 terms in the denominator. This is a linear function. I got to use natural log on this. I can't split it up and make 2 fractions, okay? That makes sense? Well, I think this would be a composite function, right? Outside function would be the division problem. Inside function would be 4x minus 1. Definitely calls for u sub. U equals 4x minus 1. du would be what? 4 dx. Therefore, 1/4 du equals dx. Rewriting our problem now becomes 1/4 antiderivative 1 over u du. We're forcing this situation to happen. We want this to happen, then we can find the antiderivative. 1 over 4 natural log absolute value u plus c. Don't forget your plus c. A lot of people forgot that in our last exam. And then resubstitute the u, which would be 4x minus 1. plus c. As soon as you find the antiderivative, you better be writing plus c. If you totally redeem yourself and write at the very end, we usually excuse that and just count it here that you forgot it here and then you brought it in later. But I would just do it right away. We good? Pretty easy? All right, let's keep rolling. Guess we go to the next page. All right, so what can we do with this? Well, this is a new derivative or antiderivative technique. Well, let's figure out how to do some of these old style of problems with this new technique. Find the area of the region bounded by the graph of y equals x over x squared plus 1, the x-axis, and the line x equals 3. When they say the line x equals 3, that means if we graphed this function 1, 2, 3, that means we're stopping right here, right? I think they forgot to give us something though, didn't they? Or is it the right bound? I don't know. So we have to find the other boundary. We have to find where this graph crosses the x-axis, right? When would that be? That would be when, what? Y equals 0, correct? And funny enough, this is an easy problem because this is a fraction. When would the fraction equal 0? When the numerator equals 0. And so when would the graph cross the x-axis? X equals 0. So we're going to find the area under the curve from 0 to 3. Now, Mr. Bond, what if it dipped down over here and went like that? It's not going to, because we would have found another 0, right? They would have another factor up here. We would have had another 0. All right. If this was a graphical problem, or a graphing calculator problem, I should say, I could just type in x divided by parentheses, x squared plus 1, find our x-axis intercepts, and go from there, right? And honestly, then you could just set it up and do the problem with your graphing calculator. This makes you write down what you're typing in your calculator. Okay, so for us, this would be antiderivative 0 to 3 then, right? Left bound, right bound. And funny enough, I shouldn't say funny enough, I don't know why I'm saying that today. I think the graph looks something like this. I'm not going to use that as most of my graphing calculator because then I won't be able to write on here, and I don't want to do that today. Okay, that'd be what? X over x squared plus 1 dx. All right, go through the process. The denominator is 2 terms. It means I'm not splitting it up. I can't take that to the -1 power. Then because I can't distribute the x through that exponent. That's not going to happen. Probably use some, huh? Let's try it. du, would that be 2 dx or 2x dx, I mean? Well, that's convenient because we have an x dx. That's nice. So we'd have 1/2 du equals x dx. And I think we have everything taken care of. Antiderivative, 1/2 out in front. That would just be 1 up top, wouldn't it, in the numerator? And then u in the denominator, and then du. And again, I could make it du over u. I don't like doing it that way, though. So that's just me. What am I missing? Oh, new boundaries. So I almost forgot to do that, too. If we got 0 here for x, that means 1 is for u. If we got 3 for x, that means 10 is for u. Correct? Well, this problem originally started as not too nice. This is an easy problem. Okay, antiderivative of 1 over u, so it'll be 1/2 natural log of absolute value u evaluated from 1 to 10. Okay, 1/2 natural log of 10 minus 1/2 natural log absolute value 1. All right, think about this for a minute, guys. Do we need the parentheses or the absolute value around the 10? No. E to some power, does that equal 10? Exactly. It's a decimal, isn't it? e to some power equaling 10. That'd be a decimal. We're going to leave it exact then. 1/2 natural log 10 minus, all right, e to what power is 1? 0. E to the 0 is 1, right? So this is just 0. So we're done. Be careful though, they could write this another way. Remember logs, especially if we have a constant multiplier out in front, this could be natural log root 10, right? Because this 1/2 could go back into the power of 10. So be careful with that. It could be either answer. Questions on this? Leave it like that. If this was an A, B, C, D choice, they might have a decimal approximation listed. They might have one of these listed. Are we okay so far? Yeah? Let's see how okay we are. Bunch of stuff in the numerator, bunch of stuff in the denominator. Looks like the denominator is 1 power bigger than the numerator. This isn't a composite function where the clear choice of u is probably obvious, but when in doubt, I'd say maybe go to the denominator. Try and force that 1/u situation to happen. All right, try and work faster than I am. We got u equals x cubed plus x. And then du, du 3x plus 1, 2x squared plus 1 dx. Well, that's pretty convenient. This is definitely a u prime over u problem, isn't it? Okay, antiderivative 1/u du. And that would be natural log, absolute value of u. Can I just right away put x cubed plus x? Is that okay? Plus c. Again, this is just a u prime over u. Just be very careful with skipping those steps. I like setting up a u substitution. Keeps me aligned. And I'm not second guessing myself either. Okay, what about the second one? That's what I would try. Because what would du be then? Secant squared x. And we definitely have a u prime over u situation. That'd be natural log, absolute value, tangent x, plus c. Okay, you guys want to give the third one a shot? Is that one directly u prime over u? Not directly, so be careful. Minus 1 million if you didn't put plus c. Now, why would I not write 1/2 c? Because it's really 1/2 times the antiderivative, right? Then you can distribute to 1/2. Why do I not write 1/2 c? Yeah, 1/2 of a constant is another constant. It's just another constant, right? Okay. Questions on this? Are we good? Is this pretty easy or what? Give this one a shot for a second. What? I got an x dx here. I got way more than x dx up top. Change variable. Okay, u minus 1 equals x squared. Well, I can put that right here. U minus 1 can go there. Then do the problem 2 more times. One for the plus of this, and one for the negative of this. Because you take the square root, it's be plus or minus, isn't it? No, no, no. Cut your losses. Start over. Guess what we're going to have to do, guys? The powers on the top and bottom are the exact same. You're going to have to actually divide these two polynomials. Long division. And Mr. Hilsninger said you guys are going to need this someday. Well, guess what? Today is someday. X squared plus x plus 1 divided by x squared plus 1. All right, what times x squared equals x squared? 1 times x squared, 1 times 1. Subtract the quantity, right? X squared minus x squared is 0. X minus nothing. 1 minus 1, 0. So the answer would be 1 remainder x, right? Or you can say the quotient of these two polynomials would be 1 plus x over x squared plus 1. So the powers are top and bottom are the same. You're going to have to actually divide. Create this situation. We have two terms. We can use our properties integrals, break this up as a sum of two integrals. The first one will be easy. The second one, the bottom is 1 power bigger than the top. That means my u will probably be the bottom and go from there. So what we learned, if u sub is not working, cut your losses, go try a different technique. Now we have to see if we have to divide these two. All right, we can break this up. Antiderivative 1 dx. Obviously, I don't need to write the 1. Antiderivative x over x squared plus 1 dx. Okay, definitely need to use substitution for this one. So u equals x squared plus 1 du 2x dx, and therefore 1/2 du equals x dx. I have x dx here. So that satisfies this antiderivative. I'm not going to take this antiderivative until I'm taking both of them, just for fun right now. Okay, this would be 1/2 antiderivative 1 over u du, correct? Antiderivative of 1 with respect to x is x. Plus c normally, but we have two antiderivatives. This is put at the end of the second one. Plus 1/2 natural log of absolute value x squared plus 1. Can I jump straight to x squared plus 1? And then plus c. All right, so let's see here. Think about this for a minute, guys. Do I need the absolute value signs? You take any number, you square it, that's a positive number. Add 1 to that number, always a positive number. So an alternative form of this answer could be this. Or they could be feeling fancy and do something like this, couldn't they? Take this 1/2, put it as the power of the argument, then we can write that as a square root. So any 3 of these answers would be possible. Which one? I like you guys at least knowing you don't need the absolute values. Sometimes it's good to write this one also. What's your guys' initial choosing of u? I would try x plus 1 because it's inner function, right? U equals x plus 1. Du would equal 1 dx. Son of a gun, we got 2x up here though. I could have some fun and move the 2 out in front, right? 2 in front, antiderivative, I'd have u squared right now, and then du. But I needed to take care of this x. How would we do that? Oh. I wish we had an equation that related u and x together, but we can make a substitution. Change variable, yeah. U minus 1 equals x, right? Minus 1. Oh, now actually this isn't too bad now. We have 1 term in the denominator, 2 terms in the numerator. We can split this bad boy up, right? 2 antiderivative u over u squared minus 1 over u squared du. And again, some of you guys might be able to simplify that without writing this step out. That's okay, I'm writing it out. That'd be 1 over u, correct? Minus, let's save a step and write u to the negative 2 power. Advanced moves. 2 times, let's say antiderivative of 1 over u. Minus, okay, this is a normal anti-differentiation using your power rule. Add 1, divide by the new power. Dividing by negative 1 is the same thing as multiplying by negative 1, isn't it? And then plus c. Okay, 2 natural log absolute value, whatever u was a long time ago, x plus 1, plus 1 over, what do we got now, x plus 1, plus c. Yeah? What 2? Oh, this one right here? Okay. Is there another way we could write this? Okay, we have a constant multiplier out in front of natural log. That means we can go to the exponent. If we square this argument, we probably wouldn't need the absolute value, right? So it could be natural log x plus 1 quantity squared. Like so. Could happen. Okay. Questions on that?